Hello everyone, this is Ketish here. In this video, I'm going to go through the AQA Combined Science Physics Paper 2 Foundation Tier from 2019. Now this paper is 1 hour 15 minutes long and has 7 questions. And it's tested on 3 main topics: forces, waves, and magnetism. And this paper has 7 questions. So let's have a look at question number 1. Question 1 is on magnetism and electromagnetism. Magnetic force is a non-contact force. Which two of these are not also non-contact forces? Air resistance is a contact force. Electrostatic is a non-contact force. Friction is a contact force. Gravitational is a non-contact force. Tension is a contact force. Question 1.2. Figure 1 shows a bar magnet. So you have a bar magnet, which is this is the North Pole here, and the South Pole on this side towards D. Which letter shows the position where the magnetic field around the bar magnet is strongest? Now it's strongest near the poles. So near the North Pole and the South Pole where I'm putting a cross. So that would be D. Next question. When two magnets are brought close to each other, they exert a force on each other. Describe how two bar magnets can be used to determine the force of attraction and a force of repulsion. Now for the force of attraction, you could bring two unlike poles or opposite poles. So let's say unlike or opposite poles, which is north and south, close together. Or near each other. For force of repulsion, you could bring two like poles near each other. That would be north and north or south and south. Figure 2 shows some paper clips that are attracted to the permanent magnet. The paper clips become magnetized when they are close to the permanent magnet. What is the name of this type of magnetism? Now, if they are magnetized when they are close to a permanent magnet, it's not force magnetism, it is induced magnetism, not strong magnetism as well. Label the north and south poles of the two magnetized paper clips in figure 2. So on figure 2, because this is a south pole here at this end of the paper clip, the top end will be the north pole. That's why it will be attracted. It's induced here, which makes the opposite end the south pole, and then this end of the paper clip, the second paper clip, is the north pole, and then the south pole. So it alternates. That's the end of question number 1. Let's have a look at question number 2. Question number 2 is on the topic of forces. Figure 3 shows a gymnast on a piece of gymnastic equipment. The equipment consists of two bars at different heights. The gymnast exerts a downward force on the bar. What is the size of the upward force acting on the gymnast from the bar? So if the gymnast is exerting a downward force, the upward force should be equal and opposite in direction should be the same size as the downward force, because the gymnast is not actually moving, so the resultant force has to be 0. So therefore it has to be the same size so that it cancels off. What is the weight of the gymnast represented? Why is the weight of the gymnast represented by an arrow? Because weight is a vector quantity. Vector quantities have size and direction. Scalar quantities have size or magnitude only. So you don't need an arrow to display it, but whereas weight is a vector. Figure 3 shows the weight of the gymnast acting from a point. What name is given to this point? So let's have a look at figure 3 again. So in the arrow, this from there, from the middle belly button is, the arrow is actually pointing down. Why are they drawing it from there? That's because that's where the center of mass is actually acting. So the name given to this point is the center of mass. Next question. The gymnast has a mass of 45 kilogram. So mass is 45 kilogram, gravitational field strength is 9.8. Calculate the weight of the gymnast. Use the equation weight equals mass times gravitational field strength. So the mass is 45 multiplied by 9.8. That gives me 441 Newton. 441. The gymnast swings from one bar to the other bar several times. Describe how the gravitational potential energy, or GPE, and the kinetic energy store, which is KE, of the gymnast change as she moves between the bars. So how does the GPE and KE move between the bars? So if I look at the bars from the side, so let me draw it on the side here. So that's the floor mat, and let's say that's the top bar and the second bar. Right. And when the person is actually here to there, right, when they move back and forth, there is more gravitational potential energy in the tall bar and less gravitational potential energy here. And there will be, when she's moving down, GPE actually decreases, KE increases. So when she's moving in this direction, GPE is more, and there's less GP because there's a height difference. There's less height here. GP depends on the mass, gravitational field strength, and the height. So when you reduce the height, the GP is going to go down. Now that GP is converted to kinetic energy. So there is more kinetic energy here. And when she's going back up, that kinetic energy is actually reduced. So how do we write this? So here's a sample answer. Let's see if I can get rid of that. Okay, maybe. So as height changes, gravitational potential energy also changes. Gravitational potential energy decreases when moving to the low bar. As speed changes, kinetic energy changes. Kinetic energy increases when moving to the low bar. Transfer from gravitational potential energy to kinetic energy as height decreases. So the gravitational potential energy is changed to kinetic energy as the height decreases. Now, the total sum of the kinetic energy and the gravitational potential energy is constant because energy is conserved here. Next question. Falling on the crash mat reduces the average deceleration of the gymnast compared with falling on a hard surface. Explain why reducing the deceleration is important to the gymnast. Now, the crash mat helps the gymnast to slow down this deceleration. Compared to hitting a hard surface, she's going to land really hard. That means there could be injuries. So using a crash mat reduces the injuries. So it reduces the force exerted when landing. So the risk of injury to the gymnast is reduced. That brings us to the end of question number 2. Let's have a look at question number 3. Question number 3 is on the topic of forces again. Figure 4 shows two children playing table tennis. The boy hits the ball from one end of the table. Why does the velocity of the ball change when the boy hits it? Well, once he hits it, the ball will eventually, it's not going to speed up. It's actually, it has a higher speed the moment it bounces, and then it slows down eventually. That's mainly because of, there's a resultant force, which is basically the air resistance. So there is a resultant force on the ball. That's why the speed will actually change. Why does the velocity of the ball change? So velocity and speed is basically the same. If they're saying it's changing, then the number 4 can't be right. The mass of the ball increases. That definitely can't happen. The direction of the ball does not change. Well, it does change depending on which way he actually hits it. The ball has an average speed of 11 meters per second. The ball takes 0.25 seconds to travel the same distance as the length of the table. Calculate the length of the table. So the distance traveled is the speed, which is 11 times 0.25. That gives us 2.75 meters. 2.75. Next question. A table tennis ball should only be used if it bounces at least 75% of the height it was dropped from. A manufacturer tested a table tennis ball. Table 1 shows the results. The height it was dropped is 30 centimeters. The height of bounce is 25.1 centimeter. Determine whether the ball can be used. So if this 25.1 centimeter that they actually observed is at least 75% of this 30 centimeters, then they can actually use it. So let's first find what is 75% of 30 centimeters. How do you find that? Well, 75 divided by 100 times 30, or you could say I've got 30 centimeters divided by 100, it will give me 1%, and then I multiply it by 75. It's the same thing. You get the same answer, which is 22.5 centimeters. So 75% of 30 centimeter is 22.5 centimeters. Now the ball bounced actually 25 centimeters, which is at least 2.5 centimeters above. So the ball can be used since 22.5 sorry, not 22, 25.1 centimeter, 25.1 centimeter is more than 75% of 30 centimeters. Next question. Figure 5 shows two table tennis balls. The balls are different sizes but have the same mass. Both balls were dropped onto the table from the same height. After they were dropped, the resultant force on the smaller ball was greater than the resultant force on the larger ball. Explain why. Now, why would the smaller ball have a bigger, the resultant force on the smaller ball was greater than. So why would this have a bigger resultant force, right, than this? Now, because they have the same mass, remember, weight equals mass times gravitational field strength. So this smaller ball and this larger ball will have the same weight downwards. Now, because this smaller ball has a smaller surface area, the upward force is going to be smaller. Whereas here on the bigger ball, the result, the drag or the upward force, air resistance, is going to be bigger. So the resultant force, when you take away, resultant force is less. Here there is overall resultant force is more, right? So if I was to use example, so let's say I'm going to use big numbers here just to make a point. 10 Newton and 10 Newton. If the drag, because it has a bigger surface area on the larger ball, let's say the drag is 3 Newton. So the resultant force is 7 Newton there. Whereas the smaller ball has a smaller surface area, so let's say it's 1 Newton. So the resultant force is 9. So how do we write the answer? The smaller ball has a smaller surface area, so the drag or air resistance on it is less. But both have same weight, so resultant force on smaller ball is more. Next question. The thinking distance of a car depends on the reaction time of the driver. Figure 6 shows how thinking distance varies with reaction time for a car traveling at 30 meters per second. So if the car is traveling at 30 meters per second and you have the thinking distance on the x-axis and the reaction time in milliseconds, that's remember millisecond is 1,000th of a second. So this would be 1 second actually. Right? So starts from 200 milliseconds to about 900 milliseconds, and it's a straight line going up. The reaction time of a driver can double if the driver is distracted. The reaction time of a driver can double if the driver is distracted. Explain the effect of doubling the reaction time has on the thinking distance. So explain the effect of doubling the reaction time. So what will happen if you double the reaction time? Let's say if you double the reaction time from 200 to 400. And then again, if I double it from 400 to 800. So I'm going to take two different values. So what happens to the thinking distance? When the reaction time, let me make it bigger so you can see. So here, if the at 200 milliseconds, that's about 6 meters. If you double this from 200 to 400, what happens to the thinking distance? Well, that's 12 meters. So the thinking distance doubles. If you go from 400 to 800, what happens? Now that's 24 meters. So again, when you double the reaction time, the thinking distance also doubles. So again, explain the effect doubling the reaction time has on the thinking distance. The thinking distance also doubles, right? Example, when reaction time is doubled from 200 milliseconds to 400 milliseconds, the thinking distance also doubles from 6 meters to 12 meters. Now, you don't have to explain for 800 meters as well. That's more than enough for 2 marks. Next question. Give the reason why there are no values of thinking distance for reaction time less than 200 milliseconds. Well, less than 200 milliseconds, maybe people are not that fast at reaction. So they are not going to be able to react faster than that. So most people cannot react lower than 200 milliseconds. They're not that fast. A driver measured her reaction time using an online test. She did the test 5 times. Table 2 shows the results. So you have the reaction time in milliseconds, 258, 265, 302, 248, and 327. So the data is all over the place. How does the data in table 2 show that it is important that the driver did the test 5 times? Why do you need to do it 5 times? Because there's a lot of variation in the results. Since there is a lot of variation in the results, or you could say there's a lot of anomaly as well. So these are above 300 and there's 3 of them at 200 range. So you might want to repeat it so that you get somewhere all close to that 250 mark. Calculate the mean reaction time for the driver. So how do you calculate the mean reaction time? You add them up. So 258 plus 265 plus 302 plus 248 plus 327. You don't need to actually write the steps. You can do this straight in. Oops. Let me get rid of that. You can do this straight in your calculator. So this was 248. And divided by the number of values, which is 5, and you would get 280. Question 4.5. The driver is driving her car at 30 meters per second. Determine the thinking distance. Use figure 6 and your answer from question 4.4. The answer from question 4.4 is this 280. So they already said right at the start the driver was actually driving at 30 meters per second. The graph is for the 30 meters per second. So how do we find the thinking distance from the graph? So let's have a look at the graph again at 280. So let me use a different color here. So that's 300. Halfway between is 300. So 218 is basically in this line. And if I draw, let me make it slightly bigger so we can actually see it better. So that's slightly above 8 because each box is, so that's 5 boxes. So 5 divided by 5 is 1. Each box is 1. So that's slightly there. So that's about slightly, you can say it's about 8.5. So the thinking distance is about 8.5 meters. Next question 4.6. The driver applies the brakes and the car comes to a stop. The force exerted by the brakes affects the braking distance. Give 2 other factors that affect the braking distance. What are the other factors that affect the braking distance? There's quite a lot of things that we can write. Anything to do with the car, the roads, or the only thing that to do with the car is actually the speed and the mass of the car. So any of these 2 will be fine as your answer. The material of the road surface, whether it's a muddy road or a normal tarmac road, or the condition of the tires, whether it's new or old, the speed of the car, whether it's wet or icy road surface, the steepness or the gradient of the car, whether it's a hill, whether you're going downhill or uphill, the mass or the weight of the car. Write down the equation that links distance, force, and work done. So the equation that links all three of them, which should be in your equation sheet, is work done equals force multiplied by the distance, right? And you don't really have to write this bit along in the arrows along the line of action of the force. When the driver applies the brakes, there is a constant resultant force of 6 kilonewton. Now 6 kN, which is 6 kilonewton, you multiply it by 1,000 to get it as 6,000 Newton. Now because it's a 3-mark question, this should carry a mark there. The car travels a distance of 75 meters before stopping. Calculate the work done. So the work done, which is capital W, is the force, which is 6,000 times 75. That should give you 450,000 joules. The work done is measured in joules. So 450,000 joules. That's the end of question number 4. Let's have a look at question number 5. Question number 5. The sun emits all types of electromagnetic waves. This question is on the topic of waves. Then figure 7 shows the electromagnetic spectrum. So they have said radio waves, microwave, infrared, visible light, ultraviolet, X-ray, and gamma. In a vacuum, all electromagnetic waves travel at the same speed. All these waves, which is listed above here, they all have the same speed, which is 300 million meters per second, or we can write it as 3 times 10 to the power 8 meters per second. They all travel at the same speed. Gamma has the greatest frequency, right? So gamma, the waves are very close to each other, whereas radio waves, let me right, like that, radio waves are far too spread apart, like a wave. Radio wave has the greatest wavelength. Explain why it is important that the Earth's atmosphere absorbs gamma rays emitted by the sun. Why is it that important? Why shouldn't we be exposed to gamma rays? Well, gamma rays are ionizing, right? If they are ionizing, that means it can damage human tissue and it can give us cancer in the long term. So it is important that the Earth's atmosphere absorbs the gamma rays so that we are not exposed to gamma rays too much, right? So gamma rays are ionizing, so they can damage human tissue or skin and cause cancer. So the atmosphere helps to reduce the exposure Next question. Some microwaves are not absorbed by the Earth's atmosphere. Why is this useful? Now, microwaves are useful because we use it for satellite communication, right? Used for satellite communication. Some ultraviolet or UV radiation from the sun passes through the atmosphere and reaches the surface of the Earth. The amount of UV radiation that reaches the surface of the Earth can be measured on a scale called the UV index. Figure 8 shows the average midday UV index in the UK for 1 year. So as you can see from the graph, January is starting low and then it steadily increases. The maximum is in July, which is the UV index is 9, and then it goes back down to again less than 1 in December. So remember, between January, February and March, these are all three of them, including October, November, December, right? I would say is during the winter or the autumn months, and April, May, June, or between these months are usually the summer months, between April and September. Why is exposure to UV radiation harmful to humans? Right? Well, as we said before, UV radiation is also ionizing, right? It's ionizing, so can cause cancer. Compare the risk from UV radiation at different times of the year in the UK. Use data from figure 8. Right, so the risk is mainly dependent on the UV index. So UV index increases from January to July and then decreases. So UV index increases from January to July, then it decreases, right? It's high during summer months. So going back to the graph, I could say, let's pick a value. So 4, right? So January, February, and March, the UV index is actually less in these 3 months plus these 3 months, right? So UV index is less in or from October, November, December, January, February, and March to less than 4, right? That brings us to the end of question number 5. Now question number 6, remember there's 2 more questions. Question number 6, which is on forces, is actually the same question that appears in the higher tier, which is question 1. So this should actually read higher tier. So higher tier question 1, and is exactly question number 7, which is in waves, is exactly the same question that appears in the higher paper, which is question number 2. So I have done videos separately for the higher paper, so I will put a link in the description and link it to the end of this video for question number 6 and question number 7. Thanks for watching. I will see you in the next video. If you found this useful, always hit the like or subscribe so that you get to see more of this. Thank you.